So, the speaker is Frank Wagner from the Ohio State University, and he will talk to us about Torsion subgroups of groups with quadratic Dehn function.
All right, thank you for having me. So today I'm gonna talk a little bit about some recent work that I did about groups with quadratic Dehn function, and then also just talk a little bit about some future directions that should be on the archive soon. All right, so a bit of background to begin with. So recall that given a group with a presentation, a word which is written in the generators represents the identity in that group, if and only if there's some product decomposition of the word, which is to say that freely it is some finite product of conjugates of relators or their inverses. So what we're interested in here is the minimal number of such factors needed to represent the word. So that's to say, K is the minimal possible value of K. That's going to be called the area of the word with respect to this presentation. Okay. So if the generating set is finite, then we can define the Dehn function of this presentation, which is going to be this function which inputs a natural number and outputs the maximal area of a word, which represents the identity in that group and whose length is at most the input. Okay. So this function is taken up to an equivalence, this natural equivalence, which is induced by this preorder that one can put on any function from the natural numbers to their positive reals, which is non-decreasing, which says that f precedes g if and only if coarsely and up to some linear term, f is bounded above by g. Now, the reason that this is a natural equivalence to take is that given two finite presentations of the same group, then their Dehn functions are actually equivalent to each other, right? Which allows one to speak of the Dehn function of a finitely presented group, which is going to be invariant up to the choice of finite presentation. All right, so why would one care? So first of all, the Dehn function ends up being a nice invariant of this finitely presented group. It's closely tied in with the decidability of the word problem. And roughly speaking, the smaller your Dehn function, the easier the word problem is to solve. A more geometric interpretation would be that the Dehn function of the fundamental group of a compact Riemannian manifold is equivalent to the smallest isoparametric function of that manifold's universal cover. Okay, and in fact, the Dehn function gives another characterization of hyperbolicity, which is to say that a finitely presented group is hyperbolic if and only if its Dehn function is equivalent to the linear function, which sends n to n. Of course, it's already finitely presented if it's hyperbolic anyway. All right. So a few basic examples of the Dehn function. So the Dehn function of a finite rank free group is immediately equivalent to the linear function. One can see this immediately from this theorem of Gromov, which is because free groups are definitely hyperbolic. But in fact, we can see this more straightforward, where we would say that the Dehn function, if we take the presentation of our finite rank free group to be the generators are a basis and the relators is the empty set, well, then that Dehn function will be just the zero function, because the area of any word which is freely trivial is zero. And based on our definition of the preorder, every function precedes the linear function, just based on the fact that we throw in this linear term. So in fact, this shows us that Gromov's characterization of hyperbolicity there actually says that the hyperbolic groups are exactly those whose Dehn function is as low as possible. All right, for a second example, let's look at the group Z plus Z, then the Dehn function ends up being equivalent to the quadratic function, which sends n to n squared. To see this, let's take the presentation to be the natural presentation. So 2 generators and the 1 relator being the commutator. Then I claim that the area of this word is this. Okay, so first of all, notice that this word has length for n, so that's linear with respect to n, and this is n squared, so kind of coarsely this is squaring the function, right? All right, to see this, we can look at this diagram, okay? If you start at the bottom left of this diagram and you walk around clockwise, then what you end up with is exactly the word that's printed here, okay? Also, if you look at any one of these squares, if you start at the bottom left of it and you walk around clockwise, you trace out the relator. So if you start at the bottom left of the diagram, you take some path up to here, then walk around the square and walk back, that would be a conjugate of the relator. And if you do that over and over again for each one of these squares, then freely the path you would trace would freely be the same thing as just walking around the whole outside of the diagram. So you'd get exactly this word, and you would use how many factors? 1 for each one of these squares. So that would be n squared of that. Okay, so that shows us that that's one product decomposition. So that shows us that the area of this word is at most n squared. And we would need to argue that in some way this diagram is minimal or optimal, right? Somehow this is the best way we could have done this. We're not going to go into that, but that's kind of what we would have to argue. Not only that, we would also need to argue that this word is somehow the worst thing that could happen. And it ends up being that, which shows us that this Dehn function is indeed quadratic. Okay. One more quick example just for another nice picture. Take the Baumslug-Salazar group, BS12. Then I claim its Dehn function is equivalent to the exponential function 2 to the n. To see that, let's take our natural presentation for BS12. Then notice that this word has length that is linear with respect to n. The area is coarsely, roughly exponential with respect to n. And we can see that with this sort of drawing, where again, if you start at the bottom left of one of these trapezoids and walk around it clockwise, you get exactly one of these relators. And down here, if you walk around counterclockwise, you get exactly one of those relators. All right, so what this is doing is hinting at one of the main tools to study the Dehn function, which are Van Kampen diagrams. So Van Kampen diagram over some presentation is this finite labeled oriented 2 complex, which is homeomorphic to a disk. Now the labeling also needs to satisfy a couple simple properties. First of all, every edge needs to be labeled by a relator or its inverse, and there needs to be some coherence here where inverse edges are labeled by the inverse of the edge's label. Pretty natural to do that. We just want to label every edge with a generator. And every 2 cell, the label of its boundary needs to be a relator or its inverse. Its inverse is based on which orientation we pick. And I should mention that it depends on where we start reading the label. So really, this is up to cyclic permutation. So in essence, this is just a generalization of what we already saw, right? Back here in this drawing, each of these 2 cells is labeled by the relator. Oh, but if I start in the bottom one, then maybe I traced out the inverse of the relator. And if I start at the wrong vertex, then maybe I traced out a cyclic permutation of that relator. So the main lemma or theorem of this study is this lemma due to Van Kampen from the 30s, which says that any word written in the generators is going to represent the identity in the group if and only if one can construct a Van Kampen diagram over the presentation whose boundary is labeled by exactly that word. All right, so with that, if we set the area of such a Van Kampen diagram to be the number of two cells it contains, and we call the Van Kampen diagram minimal, if it has the minimal area amongst all such diagrams whose boundary is that label, well then what we could see with the same argument I was making in those examples is that, or sketching I should say in those examples, is that if we take the area of a minimal Van Kampen diagram, that'll be the same as the area of its boundary, the word labeled on its boundary with respect to that presentation. All right, so why would that be useful? Well, it gives us a different characterization of the Dehn function. Now the Dehn function, instead of being this algorithmic thing, is the maximal area of a minimal Van Kampen diagram whose perimeter is at most the input. Okay, so that allows us to take algorithmic questions and treat them more with two-dimensional topology and graph theory. Okay, now changing gears slightly, another main tool I use is S machines. So what an S machine is, you can think of them in two different ways. One can think of them as a rewriting system, sort of like a multi-tape Turing machine that works with group words instead of semi-group words, or one can think of them as kind of a multiple HNN extension of a free group. Okay. So let's do a little bit of background to what they actually are. So when you have, let's start off with two finite sets here, Q and Y, which we partition into many subsets, like as so. Well, then a configuration of this double YQ is some reduced word where we take a letter from Q0, follow it up by a word from Y1, follow it up by a letter from Q1, followed up by a word over Y2, and so on and so forth, till we reach the end of the Qs. Okay. So in essence, you should be thinking of the Qs and the Ys as being put in a specific order as so. So an S rule on this YQ, this hardware, I would call it YQ, is something of the following form, where in essence, you are taking Q0 and you're turning it into this word A0, Q0 prime B1, where AIs and BIs sit inside are words written in the correct alphabets. Now we also assign some domains to theta, like Y of theta and Q of theta. Q of theta is clear, it's just all the letters that are on the left side of the arrows, but Y of theta is a little more mysterious. It's basically what letters theta can work with. Okay. And so what is the point of this? Well, to apply theta to a configuration, what we do is we check that every letter from this configuration is something that theta can work with. And then we make the changes exactly like it says up here. Right? So we replace each thing on the left with the thing on the right. And then we make any necessary reductions or trims so that the resulting word is again a configuration. Now with that comes some nice inverse rules. So given some rule theta, you can define its inverse rule by basically just switching the arrows and saying, great, turn things back around to the way they were. And that will have this nice coherence where if you apply theta, then you apply theta inverse, you get back to where you started. Okay, so then an S machine is going to be this triple where you've got Y and Q, and you've got some symmetric set, finite symmetric set of S rules. Finite being important so that everything is finite in the end. And then a computation of this S machine is just going to be apply a rule, apply a new rule, and keep going till you reach some point that you stop. Okay. All right. So how does this have to do with groups at all? That's a good question. So what we're going to do is we're going to associate some groups to this S machine. The one we're going to discuss, the only one we're going to discuss here is this group M of S. So M of S is going to have this generating set Y and Q, which we already knew are what those were, and R. And what R is it you take each rule and you take many copies of it. Now, how many copies of it? The number of however many partitions you've put on Q and Y, right? So you put these down and we subject it to these relators, which is to say that theta I should commute with letters that theta is allowed to interact with, and that theta I, well, almost up to this change of index, commutes the left side of the arrow to the right side of the arrow. Okay. Now, of course, what was the point of changing this index? It's so that we enforce the correct order upon the letters so that things actually are a configuration at the end. Okay. So why is this a group associated to the S machine at all? Well, because it simulates the work of the S machine. What I mean by that is if we are given any computation of the S machine, you start off with one configuration, you apply a rule, apply a rule, apply a rule, get down to the last configuration, well, then that will be able to be seen inside of a Van Kampen diagram over this group. Here, the bottom label, the label along the bottom line would be W0. Now, if I use the relators that we have, I can turn Q0 into maybe A0, Q0 prime, B0, B1, which is exactly what the rule does. So I can stack these things up, and along each one of these lines will be written the configuration where we are, and along the sides will be telling us what rule we're applying. Okay. And in fact, given any diagram over this group, if you look at what's happening along these vertical lines, if you look at what's in between them, it will be told by some sort of computation of the machine. All right, so what is that useful for? Well, I can understand what's happening in these Van Kampen diagrams by correctly coding the S machine. If I tell the S machine certain rules that it's allowed and not allowed to do, well, then what I can do is say, if I look at a random Van Kampen diagram, I can say, well, that has to be this sort of computation, which means that it needs to look sort of like this. So I can understand things about the Van Kampen diagrams by how I construct the S machine. I kind of look at it as coding the S machine. All right, and in fact, just being able to code the S machine ends up producing some pretty fruitful results. So for example, here's one problem that I was looking at recently. So one theorem of Gromov, so some background here, is that in fact, not only is a group hyperbolic if and only if its Dehn function is equivalent to the linear function, it's hyperbolic if and only if its Dehn function strictly precedes the quadratic function. Okay. What that means is there's some sort of gap between linear Dehn function and quadratic Dehn function. There is nothing in between. No group has Dehn function n to the 3 halves, say. Okay. So that begs some class of questions. What properties, which are of hyperbolic groups, which we know and like a lot of hyperbolic groups, but what of these nice properties are carried over to quadratic Dehn function groups or small Dehn function groups? One nice property of hyperbolic groups is that all of their torsion subgroups are finite. It does not contain any torsion subgroup which is infinite. So that could beg the question, well, what if I have quadratic Dehn function group, or just a small Dehn function group? Can it contain an infinite torsion subgroup? Well, you could take infinitely many copies of Z2, take their direct product, and that could work out. So let's make this a little more interesting and beg the question of Olshansky, which is, what if we look at a finitely generated infinite torsion subgroup? Can we say anything about a group that contains an infinite torsion subgroup, which is finitely generated, maybe a free Burnside group as its subgroup? Clearly, it can't be hyperbolic based on Ghys and de la Harpe's result, but can we say anything else? Right? The only result toward this was due to Olshansky and Sapir in the year 2000, where they constructed such a group whose Dehn function was at most n to the 10th. Okay. So using this S machine sort of coding, what I was able to do was to optimize this. I was able to construct a finitely presented group, which has quadratic Dehn function and has a finitely generated infinite torsion subgroup. And in fact, we can do better. For any m and n sufficient, m can be just like any number bigger than 1. N needs to be sufficiently large and satisfy some nice properties that I want to get into. I can construct a finitely presented group containing a subgroup isomorphic to the free Burnside group B of M. In fact, this, based on the way this machine is coded, I can even make this embedding nice, right? The embedding is quasi-isometric. In fact, it's by Lipschitz. And in fact, it satisfies this congruence extension property, which I've stated up there. We don't need to get into the details. It's just that the embedding is nice. Let's put it that way. All right, so some future directions toward the same situation. So kind of glossed over it when I talked about the Dehn function of these of a group, and I was saying there was some relationship between it and the decidability of the word problem. In fact, it gives an upper bound on the complexity of the word problem in that finitely presented group. So one theorem due to Burgit, Olshansky, Reeves, and Sapir in 2002 is they were able to construct basically a Higman embedding theorem, where you take any finitely generated group with decidable word problem with some complexity, and you can embed it into a finitely presented group whose Dehn function has some nice polynomial bound with respect to that complexity. Okay, but it's not exactly perfect, right? It's n squared t of n squared to the fourth. Things get a little more complicated. So one thing, one work I'm doing with joint with Bogdan Chornomats is to reduce this Higman embedding to be just basically in terms of that complexity, right? So using new coding techniques, we are able to basically reduce this to 2 to the 2 plus epsilon, right? Which would be almost, I would say, quasi optimum. The only thing is that epsilon, and the epsilon is any number bigger than 0, I should say it that way. Second goal, I am constructing a Higman embedding theorem, which not only, so this is completely changing, generalizing the use of S machines, it will also be malnormal. So the subgroup that it is embedding into will be a malnormal subgroup of the overgroup. And it will also preserve word problem and satisfy all the properties that we had before. Thank you for your time.
Thank you very much. Any questions to Frank? Any questions?
Could you say a bit about what goes into your construction for the first theorem?
Yeah. So in terms of the, let's see, in terms of how I construct the S machine, is that what the question is?
Yeah.
Yeah. So basically, in essence, what I want is I fix a particular word in a particular configuration. Let's put it that way. So a particular word that's written back here. I wanted to find it. There it is. I fix a particular one of these, and I study all possible words that could start with certain letters of Q and end at this particular word here, right? So I study basically all possible computations which have the same endpoint. And the way I construct the rules, the only way to start at a specific place and end at another place is to have the one of these W1s needs to maybe call it W1. It needs to be some variable, some word raised to the nth power. Now, a different way of going, you could do the same exact thing, and that would be trivial. And what you would end up getting is the fact that every word raised to the nth power ends up being trivial, as long as you enforce that that final word was trivial as well. So in essence, I want to code things in a certain way so that I can study what kinds of computations can be there, and that will enforce some sorts of relators that we wouldn't have known otherwise.
Mhm.
Okay.
Any other questions? Okay, thanks. Thank you, Frank.